Hey folks, in this video, we're going to be looking at doing stoichiometry and using our friend the mole roadmap for that. Actually, a stoichiometry roadmap. There's no clever joke. Let's go on. I would like you to be able to define stoichiometry, which is a weird word. I would like you to be able to use balanced equations, which we know how to balance equations now. I would like you to be able to use those to make conversion factors. I would like you to be able to use the stoichiometry roadmap for this weird thing called stoichiometry. Let's get going. Let's talk about it. Stoichiometry. Well, these are calculations that related to the quantities of reactants and products in a reaction. Okay, so anytime we're doing measurements or calculations based on the stuff in a reaction, stoichiometry. So this would be calculating like how many moles of reactants we have, or how many moles of products we have, or maybe how many grams we have of products, or how many kilograms of reactants, their masses. Or maybe, yeah, so these things are more useful. Our masses, in fact, are going to be way more useful to us as actual chemists in a lab than moles. Why? Well, because you can't actually go to a scale or balance and weigh moles. There's no setting for that. Scales and balances weigh things in masses. So we can create a mass, and then we can do a calculation to convert that to moles and do cool stuff from there. But masses, as it turns out, are more useful to a chemist when they're actually working in a laboratory. So when would we use stoichiometry? Well, if we're going to predict how much stuff our reaction will make or a product yield, we'll talk more about yields in the future. Stoichiometry is really useful. We can do calculations to predict how much product we will produce. Or if we're trying to make a specific amount of product, like let's say I want to make 100 grams of, I don't know, water, I can figure out how much of the different reactants I would want to use, like hydrogen gas and oxygen gas. I can figure out exactly how much of those I need to combine to make the exact amount of product I want. And so there's a lot of other ways we're going to use stoichiometry, which we'll see as we go forward in life. But if this is a reaction equation and we're doing stoichiometry, we can answer questions like, if I have 100 grams of nitrogen gas, how much ammonium gas product can I make? Or we can also answer questions like, hey, if I want to make 100 grams of this product, how much nitrogen and hydrogen should I combine together? So stoichiometry is very useful for chemists actually doing chemistry. So we talked about using balancing equations. Well, part of the reason we balance equations is so that we can use them as conversion factors. The coefficients in a balanced chemical equation make up conversion factors. And so you can convert between any chemical in a reaction. Convert from a product to a reactant, from one reactant to a different reactant, using these coefficients. The units that we convert between are always going to be moles. So let's say I know moles of one reactant, I can convert to moles of another reactant if I have a balanced equation to figure out what ratio I should combine them in. So let's look at some examples about how to make those conversion factors. If I have this balanced equation, I could write a conversion factor that says 1 mole of nitrogen gas, because the coefficient is 1, is equal to 2 moles of ammonia gas, because the coefficient is 2 here. Or I could make another one that says, hey, 3 moles of hydrogen gas is going to be equal to 2 moles of ammonia gas. And because, again, I'm just using the coefficients and units of moles. Or I could say, like, 1 mole of nitrogen gas is going to be equivalent to 3 moles of hydrogen gas. Again, I'm just converting, and I'm using the coefficients as my numbers and the units as moles. And so I could make coefficients or balanced conversion factors using any balanced equation. Here I could say 2 moles of magnesium is equivalent to 2 moles of magnesium hydroxide, this product, which this guy should be MgOH2. That's not balanced out right. Anywho, we can make so many more balanced equations from this dude, and so many conversion factors from this dude, because it is a balanced chemical equation. So that's how we can do conversion factors out of a balanced chemical equation. But what's really cool here is this thing we're going to use called the stoichiometry roadmap. We previously looked at the mole roadmap. Well, the stoichiometry roadmap is like the mole roadmap, but a little bit extra. You see, it's got all the same components as the mole roadmap. It's got moles, convert to mass, convert to volume or particles. But now it has 2 different versions of that. And in between this, if we want to convert from this type of mole to this type of mole, from substance A to substance B, from our known to our unknown, we're going to need to use coefficients from a balanced chemical equation. So that's why I made such a big deal about balanced chemical equations. We need them if we're going to use this stoichiometry roadmap, which is like the upgraded version of the mole roadmap. Well, let's talk about more how about using that. It's going to be used almost the exact same way as the mole roadmap, as I said. We use it to determine which conversion factors to use when we're doing conversions. But the key difference is it allows us to convert between different chemicals found in a reaction. We can convert from a known chemical to an unknown chemical. And most problems that we encounter, we'll have to convert from a known to an unknown. So the stoichiometry roadmap is very useful for that. And again, we need to have a balanced chemical equation in order to use that roadmap, as I've mentioned. Let's do some practice with it because it is essentially the same as the mole roadmap. Let's say we want to figure out how many grams of Al2O3, this dude, we can produce from 1.09 moles of aluminum. So we're converting from this dude to this dude, from moles to grams. Well, let's pull up our roadmap and figure out how to do this. All right, the thing I already know about is aluminum. So I'm going to start by saying aluminum is my known, and I'm being asked about aluminum oxide. So I will call that my unknown. Okay, cool. Well, I'm also going to figure out, where am I starting this? What do I already know about my known? I know the number of moles. So I'm going to put a little box around that and tell myself, all right, I'm starting here, and I'm going to go to which one of these circles am I trying to make my way to? Well, I want to know the mass of aluminum oxide. They asked for the grams. So I will start in moles of aluminum. I will have to convert to moles of aluminum oxide, and then I will convert to the mass of aluminum oxide, and I will use these as my conversion factors. Pretty not too spicy, very similar to our just regular mole roadmap. Cool, so let's make that happen. So I determine which conversion factors to use. We're going to need to use that balanced chemical equation to convert from aluminum to aluminum oxide, and I'm going to need the molar mass. But wait, who do I use the molar mass of? Well, because it's on our unknown side, we're going to use the molar mass of our unknown aluminum oxide. So I have my two conversion factors. I'm ready to set up my dimensional analysis. So I will do my 1.09 moles of aluminum. My first step was to convert to moles of aluminum oxide. So I will set that up. I will use this conversion factor and get rid of moles of aluminum and change that to moles of aluminum oxide. And then I will set up my next conversion. Oh, well, let's get rid of our units here. We'll cancel those out. And I'll set up my next conversion. And so I know here I'm converting to grams of aluminum oxide. So I'll put my grams as my new unit up top and my moles as the unit to be canceled down below. Neat. And now I can see how things are going to cancel out. The only units I'm going to be left with are grams and aluminum oxide. So that looks good. So I can just multiply through to get my pretty answer. Nice. Not too spicy, right? Nah, not too spicy. So are you a dog in this situation? Or are you a cat getting, or that's not a cat, that's a snack. Man, I don't know nothing about nothing. Anywho, let's do a little bit more practice. How many liters of oxygen at STP are required for 90 grams of CO2? Why don't you pause the video and see if you can do this yourself? You've already got a balanced equation down here, so you should be able to just rock out on this. Pause it, give it a shot. Cool. Well, you pause and give it a shot. Let's talk through it together. So, what am I doing here? What do I know about? What do I not know about? Well, I have information on CO2, right? I know 90 grams of CO2. So CO2 is going to be my known substance. And O2 is going to be my unknown substance because I'm being asked how many liters of O2. We don't know how many liters of O2. We need to find that out. It's unknown. Cool. And so I know that I have a mass of CO2. We're like 90 grams of CO2. That's the one piece of actual number. That's a number with a unit on it that I'm given for this conversion. So that's where I'm starting. And I want to get to volume or liters of O2. So I'm going to work my way all the way to over here. This means I'm going to have to do 3 steps. I'm going to convert from mass of CO2 to moles of CO2 to moles of O2, and then moles of O2 finally to my liters of O2. So I will need 3 conversion factors. The molar mass for CO2. I will need to get my coefficients out of that balanced chemical equation, and I will need to use this 1 mole equals 22.4 liters at STP. Cool. So I figured out which conversion factors to use. There's one from my balanced chemical equation. There's my molar mass of CO2, and here's my 1 mole equals 22.4 liters. So now I'm going to set up my dimensional analyses. So I'm starting with my 90 grams, the thing I know, and my first step was to convert that to moles. So I'll put grams down below because we want to get rid of the units we have. And we're going to use this dude who changes grams into moles, my molar mass of CO2. And so that will cancel out my grams of CO2. Awesome sauce. Next step is I want to convert my CO2 into moles of O2. So I'll set up my next X line, and I'll put moles of CO2 because we're done talking about CO2 down below. And I'll put my moles of O2 because we're interested in oxygen up top. And so this will cancel out my moles and my CO2. And yeah, so now all we have left as units for now is moles of O2. Great. Well, last step, we want to get liters of O2, not moles of O2. So we'll use this final conversion factor to change my moles to liters. So we'll get rid of moles, put those as our units down below. Put that 22.4 liters up top. And we can see these moles will cancel out with those moles. Only units left are liters and O2. Awesome, that's what we wanted, liters of O2. So we can do 90 divided by this times 5 divided by 3 times 22.4 to give us a fabulous 76.35 liters of oxygen. Sweet. So that is our final answer, and I hope that's what you came up with. I rounded it up here to be really good about my significant figures, because we only had 3 sig figgies here. I guess it actually should be 1 sig fig. Whatever. That's the end of this video. Oh, no, what? We got even more practice? Nice. I love more practice. Let's try one more problem. Why don't you pause the video and see if you can tackle this puppy on your own. Great, you tried it out. Well, let's do it together. Let's pull up our stoichiometry roadmap for starters. We know about, we were being asked about CO2. How many molecules of CO2? I don't know. We'll figure it out. But we know about C3H8, or propane, and we've got a mass of propane. So we're going to change that to moles of propane. We'll have to change that to moles of CO2. And finally, we can change that to particles or molecules of CO2. So we'll do 3 steps here. We'll use first our molar mass. We'll use those coefficients for our balanced equation. And then we'll use Avogadro's number as our last conversion factor. Cool. So we know what conversion factors to use. Our balanced chemical equation, our molar mass, and our Avogadro's number. I think I got to change that guy. Anywho, let's plug those suckers in. So we'll start with, well, no, that's correct. We'll start with our mass of, changing our mass of propane into moles of propane, so that we can then change it to moles of CO2 and liters of CO2. So we use our molar mass first. We'll put grams in our denominator because we want to get units, rid of our units of grams, and they'll cancel out. We'll set up our next conversion. Well, we want to change our C3H8 to CO2. So we'll put our 1 mole of C3H8 down below, and we'll put our 3 moles of CO2 up top from our balanced equation. And we can see our moles cancel out now, as does that C3H8. And so we'll do our last step to change these moles of CO2 to liters of CO2. So we'll get rid of the moles, put that down below, put our 22.4, oh, I'm sorry, we're not changing into moles. Silly Winograd, we're changing into molecules or particles. So we'll put our Avogadro's number up top. And now we can see moles will cancel out with moles, and we'll just be left with our particles of CO2. I omitted writing the word particles in here because I didn't really have space. But normally, if I were being a good boy, I would. And so this gives us our final answer, which instead of saying this in particles, I will say, hey, these are particles of CO2, or more correctly, I should say molecules of CO2. Anywho, that's the end of this video. I hope you feel like you understand how to use that stoichiometry roadmap and understand why a chemist might even use stoichiometry in the first place. Well, ta-ta, have a great rest of your life.